today is lecture number 6 of the course Hydraulics. So in today's lecture, we will continue our discussion about the specific energy, which is very important concept. And then we will study about critical depth in non-rectangular channels. We will study about the occurrence of critical depth, why it is important, and also in the channel bed if we have humps or contractions, so how we can analyze the hydraulic problems. Now the specific energy diagram, this is the topic that we studied in the previous lecture. So you see, this is the diagram which is given in your textbook. Now in this diagram you can see that we studied that this specific energy, which is denoted by E, this is the sum of the depth of flow plus the velocity head. It means that we are referring the energy to the channel bottom, or the channel bed is datum. Now this concept is very important, as I explained a few applications towards the end of the last lecture, and we will continue to discuss applications of a specific energy in open channel hydraulic problems. Clear? So we have to draw a graph between the depth of flow and the specific energy. So in order to do that, the basic equation that we can write down is already written here. It's already written here in terms of the velocity and the discharge. Clear? So it means that we have to, let's say for example, we consider this portion here, the depth of flow, and then the velocity head that is written in terms of the discharge here. So this small q we use, this is considered for a rectangular channel. So as I said, that most of the concepts that we discuss and the equations that we develop, we will develop for rectangular channel. Why? The reason is that for rectangular channel, the formulas are easy to develop and we can easily understand it. Clear? As compared to non-rectangular channels. But we will generalize the concept for non-rectangular channels also. So that's why we use the discharge per unit width. Clear? So we have this discharge q. So this discharge is in CFS, cubic foot per second, or cubic meter per second. Clear? But when we divide it by the width of the channel, so this is actually the small q, that is discharge per unit width. So then the units of this q, this becomes CFS per foot. CFS per foot. Clear? And this is for a rectangular channel. For non-rectangular channel, then we have to consider the total discharge. Clear? So in here what we do is that we just consider the unit discharge per unit width. Clear? So this is the B, small b, as per our textbook sign conventions that we are following. So this is the small b, and this is the depth of flow, which we denote by y. Now you have to develop the specific energy diagram. So as we discussed earlier, how you can develop, we have to keep this q constant. You keep the discharge constant, and you can see that physically we can do this by changing the slope of the channel here. You see that we have S0 less than SC. So this is actually mild slope, as we discussed in the previous lecture. So this is known as mild slope, S0, where S0 is the slope of the bed of the channel. So this is less than the critical slope, and the critical slope, we discussed the formula also, you can calculate. So we have mild slope. You can see here on mild slope the depth that will be greater than the critical depth. Now this point here, point C, so the specific energy corresponding to this point here, this is denoted by E minimum. So this is the minimum specific energy. Later on, I will explain that this minimum specific energy is actually required to cause the flow. Clear? Now, for this minimum specific energy, we have only one depth that is existing, which is known as the critical depth. And the flow at this point here, corresponding to this minimum specific energy, we call it as critical flow. That has the critical depth. So we have the critical depth, and then the corresponding velocity, that will be the critical velocity, and the slope, that will be the critical slope. Now, other than this, if you consider any other points, for example, if I consider this point here, this energy here, E1, let's say, for this there are two possible depths. One is this Y1 and another one is this Y2. So on this curve, these are the possible depths. It does not mean that these two depths will occur simultaneously. No, for the given condition, only one depth will occur, but these two depths, which are Y1 and Y2, these are possible because they can occur for the same specific energy and for the same discharge. So that's why this Y1 and Y2, this we call them as this Y1 and this Y2, so we call them as alternate depths. These are known as alternate depths. So it means that Y1 is the alternate depth of Y2 and Y2 is the alternate depth of, these are alternate depths, Y2 is the alternate depth of Y1. Now you see that basically this specific energy curve, it gives the whole picture, all the three types of flow, the critical flow, and then you can see that above this point C, if we slide on this specific energy curve for the given discharge, the conditions are that of the mild slope. So this is actually the subcritical flow. So it means that above this point here, if you proceed in this direction, we have subcritical flow. And we defined this in detail in the previous lecture. So we have subcritical flow conditions. Now in subcritical flow, you can see here the slope is less than the critical slope. And the depth of the water in the channel will be greater than the critical depth. Clear? And you can compare this velocity head with the critical velocity head. Of course, it is smaller than this. You can see here it is here, and the critical depth, this is here. Now, at critical conditions here, we have the minimum specific energy, and we have the critical depth, and we have the critical velocity. Now, if we make the slope steep, now in this case, you can see that S0 is greater than SC. So this we call it this as the steep slope. So this is basically steep slope. So now in this case, you can see that the depth, it is less than the critical depth, and then you can see that the velocity head is more because the discharge is constant. So that's why if one component is decreasing, the other should increase so that the total sum. Okay, now in this case, you see that the velocity head here, it is more, but look at the depth Y2, it is less as we compare with the subcritical flow condition. So it means that if we slide on this curve below point C, so below point C, the conditions are that what we call them as the supercritical flow. This is known as the supercritical flow. So this is actually a complete picture, the three types of flow that can occur in the open channel. And also we defined actually the Froude number. that is commonly we are using to differentiate, and we defined that the Froude number, it is the ratio of velocity divided by square root of gyh, where yh is the hydraulic depth. But in case of rectangular channel, so for rectangular channel like this, we have this hydraulic depth that is equal to the depth of flow. Clear? So this is less than 1. Because the depth is more, the velocity should be less. This actually represents the condition of subcritical flow. So this is actually for subcritical. This is another criteria we can use. Clear? And if this is equal to 1, this Froude number, this is equal to 1, so we say that this is critical. And if this Froude number, it is greater than 1, means that the velocity will be more, the depth should be less. So this is actually the condition for supercritical flow. So we will say that the flow condition is supercritical. So this in the problem, when we solve the problems, then this will help us to analyze the problems. So this specific energy diagram, this is actually very important concept. You will see in the problems, as I tried to explain in the previous lecture and in today's lecture. So this is very helpful in analyzing the open channel problems. Now in this case, you see that several curves are shown. The reason is that this one curve that we obtained, that is for one specific discharge. If we increase the discharge, then this Q dash, this curve will be obtained. This is for this Q dash. Clear? And if we further increase the discharge, then you can see that there is a shift of the curve towards the right. So any of these curves, that is for a given constant discharge. In this case, small q, discharge per unit width for rectangular channels. And for non-rectangular channel, then it must be the total discharge. Clear? So this we already discussed. Now, in addition to the specific energy diagram, we look to this problem from a different angle, and this was known as the discharge curve. You see that in parallel to this specific energy curve, where we see the relationship of depth versus the specific energy, we keep the discharge constant. So we discussed these various concepts. Clear? Similarly, we have another angle to this problem, which is when we can see the plot of the depth of flow versus the discharge per unit width for a rectangular channel. This can be capital Q for non-rectangular channel, and we have to keep E constant. Now in this case, what we saw last time is that the same conditions as we develop in this here specific energy. So here we also develop, or we saw that the same expressions occur as they are developed. So actually this is the situation. It shows that you see that when we have the critical depth, this is the same in both the cases. You see here 2/3 of E, 2/3 of E. So when we have the critical flow, we have the critical depth that will occur at minimum specific energy. When we look to the discharge, then at the minimum specific energy, there will be maximum discharge here. So this is known as, and we develop equation for this in the previous lecture. So we will have maximum discharge here. Now this maximum discharge which occurs corresponding to the critical depth, and we have the minimum specific energy that is corresponding to the critical depth. In order to further clarify this discharge curve, this is the figure which is given in your textbook. So in this figure, we have a flow which is occurring over this broad crusted weir, because you can see the sill of this weir, it is broad, so that's why it is called broad crusted weir. In the next lecture we will discuss flow measurement devices in open channels, so we will discuss in detail this broad crusted weir. So it is shown here, and in order to keep the specific energy constant, the flow occurs from a large reservoir, so that will help us to keep this E constant here. Now when we keep the E constant, we can see the variation of the depth clear with respect to the discharge, because for example this is the discharge that can be increased or decreased by operation of this movable sluice gate. So sluice gates, they are not only used to control the flow, but they can also be, if properly calibrated, so they can also be used for measurement of discharge, just like we are using the weirs and the notches. Clear? Now in this case you can see that when this gate is completely closed, we are here, so there is no flow, there is no depth, so there should not be flow or discharge. Clear? Now when you open the gate, so what happened is that initially we have this as the water surface, a slight rise towards the gate because of the impoundment of the water, but this water will drop as the gate is opened because the flow occurs over this weir. So now you can see that when you open this gate, then what will happen? The discharge will increase because you are opening the gate, and this depth will fall. Clear? Over this here from the top it will fall, and it is possible that we have a critical depth that can occur over the sill or crust of this weir. This we will discuss in detail in the next lecture when we study the flow measurement devices, that how this critical depth occurs. But here, just for understanding the discharge curve, this critical depth will occur. And once this critical depth occur, because the depth is more, but it has come down to the critical depth, then this depth will not go below this critical depth. The depth of water will not go below this critical depth. Why? The thing is that this depth here, that will be maintained. This depth will be maintained if we do not have this gate. So the water flows over this broad crusted weir, so in that case this depth will be maintained, and this is known as the control section. Later on we will study in this lecture also that when the critical depth occur, this we call it as the control section, and this is very important. Clear? In flow measurements. So at this point here, this critical depth occurs. Now for this critical depth, the discharge is actually maximum. That's why we are interested in this. You can see here we have maximum value of this Q by Q maximum. Actually it is a dimensionless discharge curve. So Y by E, and we have Q by QE. So independent of units. Clear? A dimensionless form of the discharge curve. But you can see here that the maximum discharge occur at C, that is corresponding to this critical depth. Now in this case, what you can see that as long as this water strikes this gate, so what will happen, that the depth upstream here, that will be the subcritical depth, and the depth downstream, means below this gate, so that will be the supercritical depth. That's why you can see here that we have this discharge curve that we see here in this figure, that we can draw by keeping the specific energy constant. So this is the discharge curve. We will solve a problem on this, that how we can use this discharge curve in the analysis of open channel problems. You will see the importance of this and the specific energy. Clear? So this is the discharge curve. Now we try to solve one or two problems, the concepts that we have developed so far, how we can apply them to analyze the problems. So this is problem 10.25 in your textbook, a flow of 90 CFS. is carried in a rectangular channel. We have rectangular channel that is 10 feet wide. The width is given at a depth of 1.6 feet. So the width and the depth is given, the discharge is given. If the channel is made of smooth concrete, now the Manning's N is given. Find the slope necessary to sustain uniform flow at this depth. So now this first part is very easy. We have to just calculate the S naught, the slope necessary to sustain the uniform flow at this depth. So when we have to solve this problem, let's say we assume this is case A. So in the case A, we have to calculate this S naught. That what is this S naught? We are given a rectangular channel, so sketch the channel so that we can visualize it. Now this is the situation given, that we have a rectangular channel. This width is given, so this is the small b, and this is the depth which is also given. So this depth, it is 1.6 feet. So this is 1.6 feet. This is the depth of flow, and this width of the channel, this is given as 10 feet. Now we have to apply the Manning's formula. Manning's roughness coefficient is given. Remember, I told you that we can analyze the open channel flow problems using the Chezy formula also. But in this text, we will as per our textbook, we will apply the Manning's formula, and I give you the reasons that why we will all the time apply the Manning's formula to solve the problems. Clear? So now in this case, the Manning's N is given. S naught we have to calculate. So we have this Q is equal to AV, the discharge. Discharge is given. So Q is equal to AV. Either you can write down the discharge formula for the Manning's equation, or you can write down the velocity equation. So that should not be an issue. For example, the area A, the flow area, that we can calculate. So this will be equal to rectangular channel. So simply B times Y, and the values are given. So we have this 10 into 1.6. So this will be equal to 16. 16 square feet is the area, flow area. Take care of the units. Now we can calculate the velocity. So the velocity will be equal to discharge by the flow area, and the discharge is given in this problem. The discharge, that is equal to 90 CFS divided by 16. So the velocity, that is 5.625 FPS, foot per second. Now that we have calculated the velocity, so we can write down the Manning's formula. Now take care of the system of units, because the Manning formula is not the same. So in the British gravitational system, the problem is given in BG units. So in this case, the formula in terms of the velocity is 1.486. V is equal to 1.486 divided by N. N is the Manning's roughness coefficient, or Manning's N, and this is equal to hydraulic radius, RH 2 by 3, and S naught 1 by 2. Now in this case, RH we need to calculate. So now this RH, the hydraulic radius, we already know that this is area, flow area, divided by the wetted perimeter. So the flow area we have calculated, it is 16 square feet, and then divided by the wetted perimeter is the width of the channel plus 2 times the depth, that portion of the channel which is in contact with the liquid, that is the wetted perimeter. So we have 10 is the width of the channel plus 2 times the depth. So we have 2 times into 1.6. So this will give us the hydraulic radius. So this hydraulic radius, this comes out to be 1.212 feet. Now we need to just put values in this Manning's formula. So just you need to put values in this Manning's formula here. So we will get S naught 1/2. This will be equal to 0.0533. Everything is known, just S naught is unknown, so you can calculate. And from here, S naught, the channel bed slope, this comes out to be 0.00284. So this is actually the answer. This is the slope necessary to sustain uniform flow at this depth. Clear? Now the next part of the question is that if we continue with this problem, the next part of the question is that what roughness coefficient would be required to produce uniform critical flow for the given rate of discharge on this slope. It means that the slope that we calculated here, this S naught, so for this given rate means that the discharge is here, this one, 90 CFS, and on this slope we have to calculate what roughness coefficient would be required to produce uniform critical flow. Now when we have critical flow, so it means that we should have the critical depth. Clear? So first we have to calculate the critical depth. We should have the critical hydraulic radius, and then based on that we can estimate the n value that is necessary. So for that what we do is that this is, let's say, case B of the problem, or part B, whatever you want to write down, part B. So in this case now we have to calculate the Manning's n, that what is the value of this Manning's n. Clear? That is to produce uniform critical flow for given discharge on this slope. So now we have to calculate the small q. Q is equal to, because we need to calculate YC. So YC formula is that in terms of small q that we develop for rectangular channels. So Q is equal to the total discharge, capital Q, divided by the width of the channel. And this will be equal to 90 by 10. This is given as 90. And the width of the channel, that is 10. So we have this 9. This is 9 CFS per foot. This is small q. Now we can estimate, we already know that this q, that is equal to square root of g into yc cube. G into yc cube. Now from here we can easily calculate the critical depth. So yc will be equal to q square divided by g into whole power 1 by 3. So if you put the values, take care of the value of the g, system of units. So this will be, let me write down, this will be equal to 9 square divided by 32.2 divided by 32.2, and this whole power 1 by 3. So now from here we can easily calculate this YC, and this YC is then equal to the critical depth, that is equal to 1.36 feet. 1.36 feet. Now we can calculate the critical velocity. So the critical velocity, that will be equal to the discharge divided by the critical depth. So this will be equal to 9 divided by 1.36. So this is equal to 6.62 foot per second. This is the critical velocity, 6.62 FPS, foot per second. Now we can easily calculate the hydraulic radius corresponding to this critical flow, because in the Manning's formula we have to calculate this now for the critical conditions. So this will be equal to 10 into, what is the critical depth? 1.36. So 10 is the width of the channel into 1.36 is the critical flow area, divided by 10 is the width of the channel plus 2 times the critical depth. So that is equal to 1.36, and this will be equal to 1.06 1.069 feet. Now in this case 1.069 feet is the answer. So now we can apply the Manning's formula. So we have this critical velocity that will be equal to 1.486, take care of the system of units, 1.486 divided by n into RH 2 by 3 into S naught, and this is critical, clear, S naught 1 by 2, which we already calculated in the case. So now in this case, when you put the values, you just solve this. The only unknown is n, so you will be able to calculate. Yes, yes.
सर ये critical velocity क्यों YC under root के बराबर नहीं थी?
Critical velocity here Q divided by YC. स्क्वायर रूट में डाल दें, स्क्वायर रूट तो नहीं है
सर. वो हम लोगों ने जो कंडीशन ड्राइव की थी सर, उसके लिए सब क्रिटिकल के लिए, सुपर क्रिटिकल के लिए और क्रिटिकल के लिए
ये इक्वेशन यहाँ पे देखें, दिस इज इक्वल टू VC, सो VC इज इक्वल टू अंडर रूट ऑफ G, दिस इज GYC.
ठीक है सर.
Here this is Q, so this is Q. Q is equal to velocity into the depth, should be the width, but the width comes here.
ठीक है सर, thank you sir.
So now n is equal to 0.01251. This is now the Manning's n, or you can say that the roughness coefficient that would be required to produce uniform critical flow for the given rate of discharge on this slope. So this is how we apply the equations that we developed in the previous lecture to analyze the flow problems. Now let us continue with this for our practice. This is now problem 10.27. So it says that water flows with a velocity of 6 foot per second and at a depth of 3 feet in a wide rectangular channel. So first we have to determine that is the flow subcritical or supercritical. First we have to determine that the flow is critical or supercritical or subcritical. Now in this case, if I consider this is case A of the solution or part A, whatever you call it, So in this part A of the question, we have to determine that is the flow subcritical or supercritical. Now we are given the velocity here 6 foot per second, and we are given the depth of flow. So now if you remember in the previous lecture, we draw a table where we discuss the different characteristics of the three types of flow. So in that case, if you remember, we studied that we are given the velocity head, the velocity is given, we can calculate the velocity head. Let me write down, then you will be confused that what is this. So we have v square by 2g. This is v square by 2g. So now you put the values. V is given, that is 6. So this is given as 6 square divided by 2g. So take care of the system of units. So this is 32.2, the value of g. So now we calculate this velocity head. This comes out to be 0.559. This comes out to be 0.559 feet because it is head. So it has the units of length. Similarly, we are given the depth. So we calculate y by 2. So this is equal to 3 divided by 2, which is 1.5. Now, if you remember, we studied that is this v square divided by 2g, which is given as 0.559. So you can see that this is less than y by 2, which is 1.5. So when the velocity head, it is less than half of the depth of flow, so this is known as subcritical. So it means that this is the condition of subcritical flow. If both are equal, this is the condition of critical flow. So when v square by 2g, it is less than the half of the depth, so we say that we have subcritical flow. So now part A solution is that we have subcritical flow for the given conditions. Clear? Now the next question part of this problem is that find the alternate depth for the same discharge and specific energy. So if we have the same discharge and we consider the same specific energy, then what is the alternate depth of this? Means that one is this depth. This is one depth of flow which is given to us. So what is the alternate depth of this? That is possible. Clear? For the same discharge and for the same specific energy. So we can solve this problem by different ways. Let us first try to solve this. This is, let's say, part B of the question or case B, or you can write down part B of the question. So now in this case, we have to calculate the alternate depth. One depth is already the 3 feet, which is given here. So what is the alternate depth for this? For the same discharge and same specific energy. So now we can write down the specific energy. So the specific energy E, that will be equal to y plus v square divided by 2g. Now you see one thing we can easily, if we understand the problem and our concept is clear, so the alternate depth that we are trying to find out must be less than 3 feet. Why? Because this 3 feet, we determine the flow condition is subcritical flow. So it means that the alternate depth that we want to calculate must be less than the 3 feet and must be the supercritical depth. Because for the same specific energy and same discharge, the two possible depths are, one is the subcritical and the other one is the supercritical. Because for critical depth, there is only one depth. So that's why here in case B, we have to calculate this alternate depths, correct? This is what is asked, that you calculate alternate depth. Now, one thing, I don't know what is the value, but one thing is sure, that this alternate depth must be the supercritical depth. This must be the supercritical depth. How I know that it must be the supercritical depth? Because we already determined in case A that this 3 feet, so this is corresponding to the subcritical flow condition. So that's why the alternate depth that we are now trying to calculate must be the supercritical depth. And if your answer to be correct, its value must be less than the 3 feet. Let us see what we get. Now we have the specific energy, which is given E is equal to Y plus V square by 2G. So we already know the depth there, which is given as 3. Because specific energy is same, so we can easily calculate for the given case A. So it is 3, and the velocity head we calculated 0.559. So this will be the same for both the depths, clear? Same specific energy. So this is now equal to 3.559. This is equal to 3.559 energy. So that's why it is feet. Now we can calculate the discharge if you want. Now in this case, this will be equal to E. E will be equal to Y plus Q square, this is Q, divided by 2G into Y square. Now we have calculated the specific energy, the small q that we can calculate, clear? It is how much small q we can calculate. This will be equal to V into Y, and both are given. What is the velocity? 6. So this is given, and what is the depth? This is given. Because the discharge and the specific energy, they are the same. So this will be equal to 18. This will be equal to 18 CFS per foot. Clear? So now this equation can be written as E is given. So we have already calculated here. See, so 3.559. This is equal to 3.559. This is equal to the depth of flow that we have to calculate. Plus we have this Q, which is 18. So this is square divided by 2G. Take care of the system of units. So this will be equal to 32.2. This will be equal to 32.2 into Y square that we have to calculate the alternate depth for the same specific energy and same discharge. Now this Y we have to calculate. So now when you solve this here, you will get this equation. What will be the equation? The equation will be equal to Y cube minus 3.559. This will be equal to 3.559 into Y square plus 5.031 equal to 0. This is now the equation. So this is a polynomial, and now it will have 3 roots, and one of the root is 3 feet. One of the root is 3 feet. So when you solve this equation, so what you will get? You will get 3 roots. One is already 3, which is given here. This is already 1 is this root. The other that you will get, that will be equal to 1.031. 604 feet, and the third will be the negative root. So that will be equal to minus 1.045 feet. Now, as we already know that negative depth is not possible, this is physically not possible. So this is physically not possible. So now the correct answer is this one here. This is the alternate depth, 1.604 feet. This is our solution to this part B of the question, that what is the alternate depth. You can see it is less than 3 feet. So this is the supercritical depth, that is for the same discharge and for the same specific energy. Now we have solved this problem, but let us try to look to this solution from another angle. There can be alternative solutions, still we should get the same answer. So let us try to solve this problem from a different angle. Now we can calculate this YC here, the critical depth. We know that the critical depth, that is equal to 2 by 3 times the specific energy, 2 by 3 times E. Clear? So now you can calculate, this will be equal to 2 by 3 times E, that is the same. So this is 3.559 that we calculated, 3.559, and this will be equal to 2.37 feet. So we have 2.37 feet, this is the critical depth. So why we say that is the supercritical depth? If you look here, this depth is 1.60. So it is less than this here, 2.37. That's why it is the critical depth that we write down here, that this is the supercritical depth. Clear? Now in this case, we calculated this YC. So we can calculate Q maximum. We can calculate Q maximum. So what will be Q maximum? This is equal to square root of G into YC cube. So you can put the values. So this will be equal to 20.7. This will be equal to 20.70 CFS per foot. 20.70 CFS per foot, unit width, discharge per unit width. Now we can calculate Q by Q maximum. So we can calculate Q by Q maximum. So what is Q? Q is given, clear, 18. So that is 18. And Q maximum we calculated here, 20.70. We have 20.70. So now Q by Q maximum, this is 0.869. 0.869. Clear? Now for this Q by Q maximum 0.869, I go to the discharge curve. You see, I go to this discharge curve here. So this is what I have calculated, Q by Q maximum. Correct? I have calculated Q by Q maximum. Now what is the value? The value is that 0.869. So this will be half here. This will be 0.9. So we have 0.8, this is 0.9, and this is 1. So 0.869 means that it will be somewhere here. So you go up here. You just extend this vertically here. And now from this figure, you read y by e. So you extend here horizontally. You extend here. Now this is 0.4 and this is 0.6. So somewhere in the middle, this will be 0.5. This will be 0.5. So it is less than 0.5. Clear? So y by e less than 0.5. So this value here from the figure, clear? From figure, this for q by q maximum, this y by e, this is approximately, you can read that this will be equal to 0.44. 0.44. So now that y by e is 0.44, e is already known. We have calculated, you can estimate this y. So y will be equal to 0.44 times e. So this will be equal to 0.44 times e. What is e? 3.559. This will be equal to 3.559. So from here, this y will be equal to 1.566 feet. So now this is the depth. Now 1.566, here it is 1.604. So it is close. This is because you need to read these values correctly from the graph. So this depth is 1.566. Alternatively, we can also look to this from another angle. For example, what you can do is you can calculate this y by e. You can calculate this y by e. So what is y? Y is given this 3 feet. We can calculate this as 3, and then e, that is already 3.559. So we have 3.559. From here, this y by e comes out to be 0.843. 0.843. Now in this case, this 0.843, you see that for critical condition, what was the situation? That for critical condition, this y by e ratio, that is equal to what? That is equal to how much? This y by e. For the critical condition, this y by e, that is equal to 2 by 3. Means that this is equal to 0.666 something. If you divide this, so let's say this is equal to 0.67, correct? So now this y by e, this is greater than that, greater than 2 by 3. What we see is that this is greater than 2 by 3. Greater than 2 by 3. Let me write down again to avoid any confusion. This is greater than 2 by 3. So when it is greater than 2 by 3, what is this condition? This is condition for subcritical. This is condition for subcritical. Even your case A can be from here. See, this is subcritical. Greater than 2 by 3. You see, this is for critical. This is the situation for critical. which we already proved before. So now this y by E is 0.843. Greater than this, it means that in the first part, the flow is subcritical. Alternatively, we can prove like this. We proved that in here, V square by 2G is less than half of the depth. So we say subcritical flow. But from here, you can also see that this 0.843, it is greater than 2 by 3. So we have subcritical. Now for this y by E 0.843, I go back to the figure. Clear? So I go back to the figure, and what is the value of y by E 0.843? This is 0.8. Clear? This will be, let's say, half of it. So this will be 0.9. This will be 0.9. And now what is our value? 0.843. Clear? So this is 0.85 and this is 0.84. Let's say this is 0.84. So this you extend here and then you go vertically down here. And you can read Q by Q maximum. You can read Q by Q maximum. And you can read this y by E here. You see the same problem, alternative solution. So now from here you come y by E 0.843. So what we can write down here, that from the figure we have Q by Q maximum that is approximately 0.865 and this y by E that is approximately, you can say approximately 0.45. Now this 0.45, it is less than 0.67. You can see here it is less than 0.67. So that's why this is corresponding to supercritical flow. That is corresponding to supercritical flow. Now from here, y will be equal to E times 0.45. And this will be equal to, what is E? 3.559. That is equal to 3.559 into 0.45. This is equal to into 0.45. So now from here, this depth comes out to be 1.602. 1.602 feet. This is what was the solution required. So 1.602 feet, or from here 1.566, or from here 1.604 feet. So approximately we are getting the same result. Clear? So this is how we solve the problems and we apply the basic concepts. So this helps us to analyze the open channel flow problems. Now the next topic, that is the critical depth in non-rectangular channels. So you see, so far we have studied the specific energy with respect to the rectangular channels, and now we extend this concept to analyze the non-rectangular channels. So now actually the concepts, they are the same, but now instead of the small q, we will use the total discharge. Now this we have to use, and this has to be kept constant if you want to see the relationship between the depth of flow and the specific energy. So you can see that we have the same concepts applied here. So we can draw the specific energy diagram, and it will have represent the three types of flow. We have the subcritical flow. You can see here in this zone, the depth is more, the velocity head is less, and we can have the supercritical situation where the depth will be less. You can see here the depth will be less and the velocity head that will be more for subcritical flow condition, and we can have this is the critical depth. Clear? This is YC here, and this is the velocity head, which is equal to half of the depth of flow. Clear? Now in this case we have the discharge, and if you increase the discharge, then there will be a shift in the curve, and still if you further increase the discharge, so in that case you see that only the shape remains the same of the specific energy diagram, but there is a shift when we change the discharge. So when we increase the discharge, you can see that the curves, they are moving to the right. And again we have the critical conditions. So you see here, this is the critical point here, for which we have the critical depth plus the critical velocity head, and because we change the discharge, so that's why the critical depth is then here for this curve, and then for this curve it is here. Why? Because the critical depth depends on the discharge. So when you change the discharge, then the critical depth will not remain the same. Clear? So that's why you can see here, and we have this critical state, and above this on the curve we have the subcritical flow range, and below the critical condition we have the supercritical flow range. So the basic idea, the concept, that remains the same, that does not change. But in the rectangular channel, for simplicity, we consider this Q is the discharge per unit width that we divided by the width of the rectangular channel, and we develop the specific energy curve that can help us to visualize and analyze the problems. Clear? This is the depth and this is the width. But now for non-rectangular channels, then we have to use the total discharge, and that we have to keep as constant when we want to see the graph of depth of flow. So the specific energy versus the depth of flow, the specific energy versus the depth of flow graph that you want to see, we have to keep the total discharge as constant. Now we will just develop some equations that will be applicable just like we develop for the rectangular channel. So we will proceed with this, and we will consider a non-rectangular channel, which is shown here, that has a depth y, the flow area a, and it has the top width t now, which is the width of the flow area at the top. So now for this we will develop one or two simple equations then that we can use when we solve the problems that includes the non-rectangular channels. Clear? So we take a break, then we will continue with this topic.